First, the abstract for today's presentation. It's going to be focusing on a fascinating area of railway substructure and geotechnics. This topic relates to the prediction of track degradation. We know that that is beneficial to us in the railway industry because of its influence on track safety and being able to plan maintenance strategies. Our speakers use logistic regression and gradient boosting machine procedures to predict defects for inspections, as for next inspections to be repaired. In addition, our speaker today is going to describe his use of GPR, ground penetrating radar data, and the use of a variety of other data sources to develop a model to predict track degradation. The model that will be discussed today is part of a larger decision-making framework that generates predictions and prioritization of track maintenance that railways can use to select their own thresholds according to their own budget and maintenance preferences and expectations internally. Now it's my great honor to get to introduce today's speaker, Dr. Carlton Ho. Dr. Ho has a BS, MS, and PhD from Stanford University. He's on the faculty of UMass Amherst presently. Before that, he has been at IIT up in Chicago and at Washington State University. He's been a visiting researcher, a scholar at a variety of locations that include the U.S. Geologic Survey, University of Edinburgh, and Tanji University. His expertise is in railway, geotechnology, and he specializes in static and dynamic behavior and performance of ballast and subballast. Dr. Ho has served on many technical committees, including TRB's Committee AR050, Track Structure System Design and Maintenance, where I've been fortunate to interact with him over the past 10 years or so. It's my great pleasure to introduce a great personal friend and a friend of Railtech, Dr. Carl Ho, to give today's seminar, Data-Driven Methods to Predict Track Degradation. So it's all yours.
Thank you very much, Riley, for that wonderful introduction. I don't think I can merit that kind of praise, but I really appreciate that you and Chris have invited me to come here to speak, and that we're really looking forward, I'm really looking forward to interacting with all of you. I just want to start off with this photo of the slide. This is our official UMass format for presentations, but I think it's nice because it actually shows where the engineering quad is. It's the tall building at the top. Let me see if I have that. Whoops, sorry. This tall building here is the Du Bois Library, but over in this area is where engineering is located. This is looking northward, and if you've heard Chris Parkin talk about where he's got this wonderful Massachusetts house, it's right over in this area here. This is Sugarloaf and Greater Sugarloaf, and historic Deerfield is behind there. The Connecticut River flows down this direction, and he has a nice house nearby, so I hope to be able to tap his resources from time to time. The campus is one of the land-grant schools, just like U of I, and so it has a similar history. The agriculture in the area is predominantly tobacco and corn. Those are probably the two biggest crops, also squash and some asparagus, but those are the main things. And also dairy, although dairy has been diminishing over the years in the area. The other big agricultural crop, and you may not think of it as an agricultural crop, is lumber. And you can guess that, it's heavily forested, but during the late 1800s and early 1900s, it was pretty much all harvested. And these hills that you see have very little old growth wood, but it's starting to come back in time. I want to also mention a little bit about the history of UMass, and I also want to, in the process, I'll acknowledge later on all the people who helped participate on this, the material in the presentation. And I want to make sure that it's understood that by no means am I taking credit for all this work. Matter of fact, being a professor, I probably did very little of the work. The graduate students and the cooperating entities who helped provide the information probably did the lion's share of the things that go into this presentation, and I really have a great appreciation for all that they have done to help in producing this research. I'd like to point out that I will get to that appreciation at the very end of the talk. And so hopefully I won't take too long and we'll be able to get to it in a reasonable time. UMass has a long history in railroad research, and particularly just Ernie Seelig, and I'm sure that you're all familiar with Ernie's textbook that has come out. There's two texts, the main text that he came out, but Ernie started research in ballast in 1978. And he's worked with a lot of very important people in the field. And through the process, you probably recognize some of the names like Ding-Ching Lee and Jim Hyslop, Steve Prismer. I could go on, and I don't mean to leave anyone out, but Ted, I better mention Ted Sussman. But there are other people who have been working with him and have contributed an awful lot to the discipline. I was very fortunate to start working with Ernie after I arrived at University of Massachusetts in 1996. And when he retired in 1999, largely due to health reasons, he and I worked together and continued the rail research, and that's how I really got into starting working on ballast problems. I continue to do that and collaborate with researchers all over the world, and I think that it's largely in part because Ernie and his leadership and the impact that he made in the discipline. I really am grateful for that. I just want to talk a little bit about what I'm hoping to present. Now, you notice in the title I talked about using database methods to try to make decisions with respect to track degradation, or more so ballast degradation. And the idea of this came out from a couple things. My PhD research was in probabilistic analysis in liquefaction, so I had a background in trying to understand how can you do hazard and risk analysis for earthquake events. I took some of those principles and tried to apply them to the idea that the data that you get from different sources could give you a window as to how to make decisions and predictions as to what's going to happen with respect to the degradation of the track. And that can in turn result in understanding when do you think you need to do maintenance. I think it's important to understand that the idea is to do maintenance not necessarily on a corrective or reactionary approach, but more on a predictive to be ahead of the curve. And that's just to make sure that you can do the maintenance so that tracks do not have to drop their speed or be taken out of service because something catastrophic happens. I think I'd like to go through that by talking a little bit about the correlations we did to evaluate the track settlement and tie that into geometry indices, and to look at what these subsurface conditions could tell us about the probabilistic models. And then I just wind up with a conclusion. Just a little bit about the benefits for the need for ballast track maintenance. Basically, the idea is that we want to make it safer for the passengers and trains, but also we want to make it so that it's comfortable too. And it's kind of both of these. And you think about what the requirements are with respect to geometry. They're often tied to the speed in which the trains are allowed to go. And we, as I said before, we want to look at preventative maintenance, maintenance that you do to make sure that you don't have a drop in class of the rail, that you don't have a situation where the train has to be closed or not used to its greatest extent. There are financial considerations and consequences for that. We also want to see if there's a way that you could look at the prediction of the degradation so that you don't have to do unnecessary maintenance. In other words, just because something has been scheduled for every 2 years or every 4 years doesn't mean that that's when you should be doing that maintenance. It should be done because you expect for that maintenance to be required soon so that you go in and do it when it's most economically advantageous. Now, what we did was we used geometry data, and I'm sure you're all familiar with the different types of geometry data that exist out there, but we used geometry data of 300 miles of passenger revenue track, and we looked at 110 different geometry inspections from 2011 to 2020. Some of the inspections were more robust than others. You know, we know that with every inspection, you don't necessarily get every single type of measurement possible, but we would at least get some type of geometry measurement. Now, in order to do this analysis, the typical thing that you do with trying to do something statistically is you have to break it up into segments that are manageable and that can be characteristic of that section of track. So we broke it up into lengths of 200 feet. And this seemed to be either a common length or something that was close to the length that would be commonly used in other studies. And it also made it so that we could get windows as to what was going on in each segment. Now you'll notice that we have data here that shows a 62-foot mid-chord offset of the profile given at different mileposts. And the idea is that by doing this, that if we broke it up into individual blocks, we could evaluate each block and try to identify what the degradation rate was, how bad the degradation gets over time or over amount of MGT. And also we could look at it to see if we could identify where maintenance events occur. So, but in order to do that, one of the things that we know with collected data is that the collected data are not always great. They're not always perfectly aligned. That's always one really difficult situation with it. And it's not always set to measure the displacements or the whatever measurements you have in the proper fashion. So what we have here are two curves here. One is the 62-foot mid-chord offset, and the other one is the space curve. Now, I put this out there because the space curve is really what we use because we were looking at the settlement or the displacement that happened over time. You can use both, and different researchers have used both of these types of approaches, but we felt that by using the space curve, we could get a better assessment as to how quickly was this degradation occurring. There's also a lot of times there's noise in the record. We have to be able to get rid of whatever the noise is. Oftentimes that noise is in high frequency, but sometimes it's just in spurious readings. And it might be in one inspection, it might be in multiple inspections. Now here we're taking a look at a heat map that shows as a function of time, the time is on this scale starting 2011 up to 2020. And the heat map shows an increase in the standard deviation. And sort of using that as a measure of the displacement. What you can see here when you look at the data, that some places it looks like, yeah, there was continued degradation, then every so often it gets corrected, and then the degradation starts up again. There might be some sort of intervention here, and then it continues on. Other places, the data don't seem like they match up very well. This is not uncommon, but it probably tells you at certain dates when those measurements were taken that maybe in this case they didn't have the location properly registered in the geometry car. It could be that there might have been some sort of bias in the way that it was read, or even in the way that it was recorded. And so that you have to go in, and immediately the first thing you're going to do is you're going to take out those segments. And I always have this sense when you say, oh, I'm going to take out those data, you're actually filtering out spurious data. And it's not that you're throwing things away, but it's that those things statistically do not add anything, but they actually degrade from what you're trying to figure out. What we want to do is use as much data as possible to try to get these statistical based correlations. You'll also notice that sometimes you have different rates of settlement that can change geometry indices. So it's important to look at different ways to try to evaluate out what's going on. So the first thing is we're going to take out anything that we feel is spurious, but we're not going to just do it willy-nilly. We're going to use a programmed approach that would model what one would do naturally by just looking for these things, but have it so that it automatically takes it out, so that at least the bias that's in there is bias that's put in by the programmer and not by the person who's just looking at this and saying, that doesn't look right, I'm going to take it out. And I think that's an important aspect with anything that you're going to do with filtering out what you feel is spurious data. Now here is also an interesting plot. This is the plot of the standard deviation as a function of time in years. And what you see here is that if you have an upward slope, that means your track is getting in a worse condition. This is actually one of the keys that we want to try to identify. We want to identify how does the track degrade as time goes on, and we want to be able to identify it based on there having been a maintenance intervention, and that we are getting an appropriate slope for that. So let's just take a look at a couple of these. One is, in this first one, it's easy to see. All right, we have a straight line, all the points seem to fall on that line, and then we have a drop. That drop brings down the profile standard deviation way down to a low level of below 0.2, and we're saying that we're concerned with blocks that have at least 0.25 somewhere within the block. Now we look at this next block, number 2, we do get a trend, but you'll notice that we have some drops every so often. What we want to do is we want to come up with a logical way to say that, well, this one probably is one single transition that we would look at the slope of that to get our degradation rate, but we don't necessarily want to eliminate it and say there was a maintenance intervention at this point and that this has its own slope here, because that probably is not accurate. And you'll notice that in this one here, you have some jumping, a lot of jumping back and forth. This one here, there's a lot of jumping going back and forth. And that we want to be able to come up with a logical way to say that we have an identified intervention. All right. Now, in order to do this, we need to have good space curve data alignment. So in this case here, you can see that we have two geometry measurements, one in 2011, the other in 2014. You can see some trends that seem to fit, but there seems to be a time lag. If you got rid of the time lag, you can see that there would be a good fit here. Time lag meaning not so much time, but space. I should say space lag. I oftentimes refer to it as a time lag because you could think of this as like a time history, but our time is instead of time domain, you have location domain or distance domain. And so that it allows you to think of this as a random signal that you could do signal analysis on. So in this one, we want to make sure that we can align it so that when we look to see what the change in the space curve is, that we're aligning the points properly. This can be done by doing a cross correlation and looking at the phase relationship as if each block were one time unit, and so that if you break up that as pseudo frequencies, the frequencies would be as if they were fractions of that time block. So let's say we have a 200-foot space block. To convert that into its time domain frequency, that means that a frequency of 20 would mean that you would have one frequency that's based on 10 feet. So that would be one cycle per 20 cycles per 200 feet. And so that's the way that we work that. So if you do that, you can use the phase relationship to help you adjust what these time lags would be. Now, here's something you can also do with that cross-spectral density. If you look at this, we can also use the coherence function to identify what frequencies are important to look at for these signals. If you look at this space curve here, you can see that what's predominant are these relatively low frequencies. If you think of going from 1200 to 1400 as a single time unit or single distance unit, that you probably are going to go up to about 20 cycles per block. If you look at the coherence is a measure of how good do the two signals correlate. The correlation seems to be pretty good up to 20. You'll see a little bit of a dip here, but that's probably because there's an absence of that frequency, since one of the predominant frequencies here is about at 20. And so by doing that, you can see that we can actually filter out the higher frequencies that are above that. In other words, any of the movement that's at a higher level up here, you actually don't see it because it's already pretty much at a small level that you don't have those values being something that's dominant. But what you do have at the end is you can see that there is a good correlation between these two curves, and you can see that those two curves, yes, they do seem to show that there is a displacement that's going on. Now, we were able to get the slopes of those lines, and we could relate those to the rate of change based on MGT. Now, if you did it versus time, which is what we had in the previous plot, you may not have consistent amounts of load that are put onto the track. And MGT is a good way to measure how much exposure has that track had to the traffic. And we took a look at the rate of settlement as a function of the track roughness, and you can see that we have two different regression analyses. One is a linear regression, and the other one is a polynomial regression. It's just basically a parabolic fit. It's a second order. And you'll notice that for both this passenger track A and the passenger track B, both of these had better fits with that polynomial regression. This one's just slightly better. It goes from an R squared from 0.652 to R squared of 0.715. And this one is kind of similar. I mean, and statisticians would probably say that that's probably not that great of an R squared, but in geotechnical terms, that usually is considered pretty damn good. And it's just because it's oftentimes that there is an awful lot of scatter within the data. And you think about that these are over fairly long sections of track, over a fairly long period of time. There's a lot of data and a lot of other variabilities that may play into some of the variability that we have here. You'll notice that if we take a look at the rate of settlement in MGT as a function of the standard deviation, you see that we get really good correlation. We actually get a better R squared value. The R squared value here is 0.884, and this R squared value is 0.819. And you'll also notice that it's linear, which makes this could be a very good way to do a sort of a prediction of what the rate of settlement is based on the rate of change in the standard deviation. So this is one of the things that we wanted to look at, is that how could we use this to try to come up with a probabilistic approach. Now, what we wanted to do for identifying problem conditions is we created a label. We called it a yellow-tag defect. And the reason we called it a yellow-tag defect is that we wanted to bring sort of an alert that there may be a condition that would potentially be problematic in the future. Now, I point out that I also didn't want to call it red tag defects, because there are red tag aspects of track inspection and what happens with the track. And also the red is oftentimes, you know, indicative of something that is requiring that there's a change immediately. Yellow tag just means that you're getting close to it. What we did was we set our yellow tag defect level to be half that of what the FRA requirements were for the class track for the maximum deviation from uniform profile. And so that if you look at these curves here, it could be plus or minus above 0, right? And so let's say this is a yellow tag defect. The threshold is set at 1 inch. Then we could look that we see one time that it exceeds it here, and then over here, 2 times it exceeds it with respect to absolute value. So we could look at these and identify which blocks do we have that could be tagged as yellow-tag defects. In other words, ones that would definitely be something that would be of concern. Now, to identify these yellow-tag defects, we can do histograms, and you'll notice that the yellow-tag defect we defined, it's a binary thing, either it is or it isn't. And we're defining the yellow-tag defect as a 1. Now, you'll notice that there's a great imbalance of data. And that's oftentimes, if it's too big, it can pose a problem. But if what you have in your training data is similar to that of what's in the test data, then you should be able to get comparable results, and it should be appropriate. That's sort of a cautionary note that I want to mention. But you'll notice that as we have lower track class, we're going from 4 up to 8, you'll notice that you have very few yellow-tag defects, and you're starting to get a few more as you get to the higher levels. We'll talk a little bit about that in a little bit. Now, what we wanted to do was we wanted to relate this to other things, and it was mentioned that we did some GPR analysis, and the reason is that for 2 of the data sets, the 2011 data set and the 2019 data set, they had GPR data on this, on these. Now, I should point out that not every measurement set is going to have GPR data. Matter of fact, for definitely older sets, it's not as common, and it's still not completely common in newer sets. I think it should be part of a regular measurement. And the only reason is that you can get a lot of information from that. It's a good source for finding moisture in the track, and from that moisture, it can give you a correlation to the Ballast Fouling Index. I also want to point out that we used Rail Doctor, and the reason is that Lorem was a partner in this project, and that Rail Doctor is the software that they use. They provided the data that we used in here, so it made the most sense to use Rail Doctor. I just want to point out that there are other software packages out there used with other radar GPR measurements that do the same sort of thing. We just wanted to make sure that we were doing it using Rail Doctor, but also at the same time, the team had a lot of experience working with Rail Doctor, and as a result, we had confidence that we were getting good correlations with the Ballast Fouling Index. This is a, I don't want to call it a heat map, but it's actually a plot that shows, based on color, what the correlated Ballast Fouling Index was for different locations. If we look at the chart, this would be in line with the track, and you can see that this would be the right channel of the track measurement. So in other words, it would be a radar antenna that's off to the side, to the right side of the train. I think it was done on a high rail vehicle. And this would be an antenna that's at the center of the high rail vehicle, and this was on the left side of the high rail vehicle. So you can get an idea as to what's going on underneath the track and also what's in the shoulder. And so you get a good measure. And then these were the measures that were taken at the different locations in the blocks, and the average values that you had for that entire block. So this would be a 200-foot block. These are kind of the center points of each of these blocks, sub-blocks, I guess I should say. And this is the average value that you got for the block. Right now what we're doing is, I don't have it in this presentation, but we're actually looking a little closer as to what happens with concentrations if you have areas that have real high concentrations of bad conditions, yet the low concentrations over here may affect the average score. So maybe it should be a peak value instead of an average value, but we were using average values for this analysis. And so that we could get an average value for each of for the center, left, and right, and then you could actually get an average value for the entire block, which is what we did here. Okay, so what are some of the independent variables that we might use in this analysis? Because really what we want to do is have all the different types of measurements that we can have and come up with a way that we can predict from those measurements what we expect the projected life of that ballast to be. So we use the standard deviation, which was basically a 62-foot mid-chord offset. The defect ratio, in other words, the ratio of maximum profile point value to the yellow-tag defect threshold. In other words, how bad was this compared to where our threshold problem would be. The standard deviation variation in the profile from the previous inspection, because what we want to do is we want to see if we can make a prediction for the next inspection. In other words, we haven't made the next inspection, but based on the inspections that we've done, can we predict what's going to happen next? The MGT, or the loading of trains between any two inspections, and the class of track that we have according to FRA standards, and the Ballast Fouling Index that was determined from the GPR data. So we have this block, these blocks here, and you can see that we could get, we could take each of these blocks and come up with our correlated parameters for each one of these blocks at the same time and try to see how they could come to make a prediction. All right, so here we are, the automatically determining of the dates of conducted maintenance interventions. Now remember, I talked a little bit about the problems with making the predictions. I'm going to concentrate on these different conditions because it's very clear that for each one of these, we can identify where that intervention occurred. And what we have here is different ways to ascertain whether or not we have it. Does that intervention show a significant drop? And we could define what that significant drop would be. And then is there a significant variability in the results that before and after that we can determine whether or not we have a condition that would be an intervention. Now, how do we go about doing it? I should also point here that if you take a look at these curves here, these look like they're easy to interpret. And matter of fact, even with this low amount of improvement, we have confidence to say that that probably was an intervention. Over here, we've got all of this variability up in this area. It makes it very likely that there were no interventions in here. It's just scattering the data. So how do we go about doing this? So what we've done is we've set thresholds. First, we look for the total number of inspections in the block. And if we have a ratio of one inspection to the next inspection that makes it less 70% of the previous inspection, that could be condition one. So we have to have at least a 30% drop. The second one is it has to be that the difference between the two is greater than 0.03. In other words, if we go back and take a look at some of these little jogs back and forth, in there, these would not be considered interventions. And you look at it, and that wouldn't make sense. But over in here, we have all of these that we have to think about and try to identify whether or not they meet that situation. Condition 3 is that we could do another test to see if we have condition where we have it be less than 90%. If it's less than 90%, it's not as much. And if we go back to this one here, this one probably was between the 90 and the 30% drop. In other words, the 70% and 90% value. This one might not have met that condition 1, but it meets the condition here is condition 3 and 4. And so that if it meets condition 4, which is that the last 4 inspections, there wasn't much of a variance, that it was on this one, there was almost no variance or variation here, that we're pretty confident that this represents a very large drop in the standard deviation, which it probably was a maintenance intervention. So then you use the second condition along with 3 and 4. So if you think about it, 3 and 4 are just a substitute for 1. 1 is, do you have a big drop? And 3 and 4 is, do you have a moderate amount of drop, but did the record beforehand be a very, very consistent value? So that's where we're getting these two conditions here. And so basically this is just a, it's something that's easy to code in, and you want things that are coded in so that you don't have to make judgments, that it automatically does it. And then you can handle a lot of data to make sure that you understand those. Okay, so you can see that here and what was done at that point. Okay, now, once we've got those interventions identified, we can determine some of those parameters that I mentioned. In other words, all of the, we can get the rate of, well, let's just think about these most important parameters, I think, are like the standard deviation, the ratio of the last defect to the maximum allowable defect, changes in standard deviation, the MGT between 2 inspections, the class of the block, and the fouling index of each block when considered when available. The logistic regression is nothing more than taking a multivariate standard regression, but using it in logarithmic form. And the reason that that's done is it oftentimes gives you a better assessment as to optimize that. And what you can do is you can optimize it by determining the greatest likelihood of these probabilities here, the product probabilities. In other words, you're taking into all of this consideration, and we can determine what's the probability that you would have all of these different conditions of X. X is just the input parameter that you would have depending on which of these inputs you have. And so what we're doing is we're trying to look to see what's the probability, can we get a good regression? So you think about it, this is nothing more than what you would do with any kind of regression, whether it's a linear regression, a nonlinear regression. We're just getting a best fit. We also use the gradient boosting method, and I should point out that, remember, what we're doing is we're using one set of data to train the model, and another set of data that has similar yellow-tag defects, a ratio similar yellow-tag defects to non-yellow-tag conditions. And we want to see what kind of performance we get by training it on one method, then applying it to the other data set. So the gradient boosting method is another technique, and it follows into a large family of statistical methods. We chose this one because it was one that was a good decision tree method. But the idea of decision tree method is that you can set up a decision tree. I like to compare this to, for those of you who are geotechnical, for doing your AASHTO soil designation, right? The AASHTO soil designation is you have questions and you answer those questions, and it's a yes or no thing, so that you branch off and you end up with what your final designation is. So basically that's sort of the same thing. That in this case, we see the first question is x1 greater than 1.5, so then it would be everything that's in the upper section up in here. So we go to the next question here is x1 greater than 2.5. And so we had x2 greater than 1.5, x2 greater than 2.5, so that leaves these two blocks here. And then we go to the last question, is x2 less than 3.0, and we end up that this is the class that we would have. It's kind of a simplified version of a decision tree, but these decision trees can get very cumbersome. As a matter of fact, the more cumbersome they are, the less accurate your prediction method is. In other words, you don't get trained very well. You don't get a very good training. But what you can do is that you can break it into smaller trees and do the repeated analysis on these smaller trees and put them together to get a common result. And what happens, and I don't want to go into the whole methodology, but basically what you're doing is you're simplifying it so that you can get a better accuracy by doing these simpler trees and getting something that allows you to get to a common result. You can make your decisions a lot better with a lot more specificity. I'm not going to go over the flow chart. Flow charts are just there. It's mostly, you're going to have these slides there so you can see how we went about and did the process. And it's basically that we had the data, we put the data in and made the data usable. Then we merged them with what other types of data that we might have available. We did cross-validation to make sure the data was appropriate. And then we trained using, well, we did the logistic regression and we did the GBM and we trained both models and then we did a comparison of the two. And the idea is that we wanted to see how did these two different methods fare, how good were the results. So basically we use these types of measurements to evaluate what how good the regression or how good the method was. Sensitivity is the number of true positives divided by the number of true positives and the number of false negatives. In other words, it's showing you how well did you predict that the true positives. The specificity is the number of true negatives given the number of false positives and the number of true negatives. And the overall accuracy is just the weighted average of the sensitivity of the specificity. Let's see, I think I have here a plot, our table. So these are actually what our predictions were. So we have true positive, the block within with a yellow tag defect that was correctly predicted. So we want to have that. The false positive is a block without a yellow tag defect that was wrongly predicted. In other words, you said that it didn't have a yellow tag defect, but it should have had one. The true negative is one that was without a yellow tag defect, but was correctly predicted. And a false negative is a block with a yellow tag defect that was wrongly predicted. You can think of this, if you're thinking about it, hypothesis testing, this goes right into the same thing with hypothesis testing, what type of error that you're predicting and how well you are predicting your appropriate value. If we look at these tables, this is the analysis that was done without GPR, this is the analysis that's done with GPR. You'll notice at first there's a lot more data without the GPR. Well, that was because we only had GPR for 2 years and we had a lot of years of data. You'll also notice that for the models that we are able to see that this here, we correctly got the true negative, and here is the true positive. So if you think about it, the diagonals on all of these are our good results. Those are the things that we want to have. The off diagonal here and off diagonal here is not so good, right? You're making an error in your prediction. You'll notice that the diagonal terms are always much larger. Now, when we think about the sensitivity is number of true positives divided by the number of true positives plus the number of false negatives. So the true positives were here, and the false negatives were here. So it's really this number of true positives divided by this here. So the sensitivity on this one is actually for without the GPR data, it was 0.87, and with the GPR data, it improved to 0.89. Now, when we have the GPR data, Well, first we have the specificity. We can see that the specificity, the number of true negatives over the false positives plus the true negatives, those numbers go way up to 1.0. And the reason is that you just have so many more true negatives, right? This is what we want. We have this true negative here, and it's true negatives plus false positives. The false positives, we have very few of them. So you would expect numbers that were close to 1. So in other words, the specificity, the ability to predict true negatives was pretty high, and one would expect that with the type of condition that we have. Now, in determining the coefficients, this is just from a regression analysis. That we've gone through the regression analysis, we've optimized what the beta values are, and you can see that without the GPR, we don't have obviously a parameter for the Ballast Fouling Index, but we do have parameters that go along all through here. A couple of things that you can note from this is that for class 6, 7, and 8, we don't seem to have very much change. And the reason is that if you think about that, for those, on those classes, the threshold, the yellow tag threshold was all the same because the FRA requirements are for them to all have the same value of the displacement. If we look at our plot here, this is the standard deviation of profile versus the class of tract, and they're basically box and whisker plots. And you can see that class 6, 7, and 8, the distributions aren't that different. We have mean values that all stay about the same, but 4 and 5 down to 6, we definitely see a change in the mean values. Well, 4 is interesting because with respect to the negative values for all of them stayed about the same, although there was a bit more variation in the lower classes. But we definitely see a trend where the mean values of the positives would decrease as we get up to the higher class tract. And sure enough, here we take a look at the class of tract, and so these are the maximum deviation from uniform profile, and you can see 6, 7, and 8 all have the same requirement. Yet for the lower classes, we see that we have differences, and you notice that we only have 4, 5, and 6 because all of our tract had 4, 5, and 6 class tract ratings. Okay, so let's consider the accuracy of the logistic regression versus the gradient boosting method. So over here we have the logistic regression, and if we look at it, I just put these up here because that way you'd have the data to do comparison with. You can see there's these are fairly similar in that we have larger values for the true negative and true positive than we do for the false negative and false positive. And similar thing happens with the specificity that they both have 0.1. We already saw this plot here. But you'll notice in the gradient boosting method, there was an improvement. Our sensitivity improved by quite a bit. So there's a comparison of the sensitivities. What we can do is we can plot the sensitivity based on what we use for our threshold. In other words, we just use 50% of the FRA requirements as our threshold. You could change that. And so this is just the percentage of whatever that classification was. And basically, when we look at that change in the classification, we can see there's a point where both the sensitivity and the accuracy all cross. Over here, you'll notice that the blue curve is the sensitivity, and as you change your threshold to be a higher level, you lose your sensitivity. You aren't able to make that prediction of a true positive as quite as easily. The specificity, though, will get better, and the overall accuracy will improve. Now, one of the things we found is that we can find a point where they cross over. And it depends on what the data are and which things that you do within the regression. But we want to just take the gradient boosting method and the logistic regression and see how they perform. So this is logistic regression. And you can see that the crossover point for that threshold is about 9%. This plot here is just showing what we would have is the blue crosses represent actual yellow-tag defects, and the red circles are predicted yellow-tag defects. And one of the things that you'll notice is that there are very few cases where you haven't predicted an actual yellow-tag defect when you by the prediction method. As a matter of fact, it almost shows that you have an over selection of that. And so you can see that in what's referred to as a confusion matrix. Oops, here. And what this does is it allows us to, we're taking a look at different mileposts and what we make as predictions. You can use this to, one, see what happens over time, and also see if there are certain times when you might have more spurious results than others. Like in here, here we had some errors in the prediction in 2018. This looks like it's about February and March. Maybe there was a reason for that, and likewise we have one. But in general, we're getting pretty good predictions. Now, what we want to do is also fit proper probabilistic probability distribution. So these are PDFs that we want to do, and we looked at a lot of different PDFs. What we found is that the Burr distribution was a 2-parameter distribution function that actually allowed us to carefully get a good distribution that could define what the behavior is. There are similarities to how it behaves. I like to say that it has a similarity to a lot of distributions that don't allow for 0 values. And that's an important part because you want to make sure that the probability distribution function, you're looking at the absolute value, and so that you want to see what that prediction would be with a proper probability distribution function. And what we did was we looked at a couple different things. One, you could adjust the location of the curve, in other words, the offset that you have on the curve, and also the amplitude and the spread of that curve, and you can use that to fit what probability distribution function that you have based on the data. So we use this to evaluate what our data were like and what kind of probability distribution functions we'd have from our measurements. And we wanted to see that how it fit with what we measured with our Ballast Fouling Index, because if we could get a probability distribution function for the Ballast Fouling Index, if this is an important parameter that we can use to make a prediction for what the degradation of the track would be, we could put that uncertainty and convolute it into the conditional probability of the rate of degradation as a function of ballast fouling. And this is just showing you that we have different, we put them into different groups. And these are just clean ballast, we said, was anything that was between 5 and 15% fouling index. We put the 5 because there was really nothing that had less than 5% fouling index. 15 to 25 are moderately fouled. I think I've got some errors in here as to what the numbers are. My apologies. I'll try to correct it, and I'll send an updated slide presentation to be put on the website so you can get it. But anyhow, we broke it into 4 different clean, moderately fouled, fouled, and highly fouled. I think actually this one, these 2 should be shifted down. I think it was 0 to 5. But what you can see is that we get these distributions, and these are the box and whiskers. We can fit these distributions to the PDFs that we have using the Burr distribution. And so that's essentially what we did. So here we have the different Burr distributions, but we also compared it with the gamma distribution, the Weibull distribution, and the log normal distribution. I think if you think about what most statisticians do is they usually use one of either the log normal, Weibull, or gamma distribution as one of the ones that they fit for values that are 0 and greater. And we just wanted to make sure the Burr was in there. And what we found was that the Burr was able to get a better curve, you can see it in here, than all of the others. The log normal was the one that tended to overshoot at a low value, and they all fit really well on the higher values of the track degradation rate, but the probability might overpredict what the low values of the track degradation rate would be. That's actually a problem because you don't want to underpredict the track degradation rate. You want to be able to predict that as accurately as possible because that's what's going to tell you whether or not you expect to have a needed maintenance before the next inspection. All right, so here's the CDFs. And what we did here is when you plot up a CDF, you probably remember this from probability and statistics, you can always plot up the discrete cumulative distribution function, and you can see that the stepwise function here matches up really well with the Burr distribution, continuous numerical evaluation and prediction. So that we felt that that was a really good way to evaluate it. And you can look at the chi-squared values here, how all of the different distributions occurred. You can see the chi-squared on the Burr distribution all seem to be pretty good. Yes?
I'll just point out your table here has the correct values in the previous.
Okay, you're right. Oh, thank you. Thank you very much. So it's here. So this one is 35 to 40. Thank you very much. It's always good to have someone who can bail me out in times of need.
The other results are really interesting, so it's nice to see that.
Yeah, so basically, I just want to say that this is just a work in progress. It's something that we're trying to do, and we want to do it for more than just passenger rail. We want to do it for also freight rail, and see if we can come up with a good probabilistic approach to make some of these decisions. Should point out that we've shown that space curve data can be used probabilistically to evaluate the conditions of ballast and track with respect to the need for maintenance. The correlations between the track settlement and the different geometry indices can be identified, and we can use probabilistic methods and models to identify when these yellow-tag defects are likely to occur in the next event. And we can also use the probability distribution function, the cumulative distribution function, to basically identify what the uncertainty is with respect to the Ballast Fouling Index and give us a meaningful way to assist in making maintenance decisions. So with that, I'd like to thank all of the people who worked on this project, particularly my graduate students, Syed Gadarzi. Some of you have been at the TRB, probably have met him, and as we know, and as you graduate students know, that we professors couldn't be anywhere without our graduate students. And I'd like to thank Hamid Kashani and Aaron Judge at Lorem Technologies for providing an incredible amount of assistance on this, and also with Jim Heislip, who used to be at Lorem Technologies, is now with HNTB. And I should put out that the three of them really were a lot of the inspiring thoughts that went into coming up with this research topic. I want to thank Mike Tracino and Amanda Kessler at Amtrak for working with us, and Steve Prismer. And always want to thank Hugh Thompson and Ted Sussman, not just because of the funding, but also because they provided a lot of really good technical advice and suggestions and really helpful and had very valuable insight as to what we could do to make this model better. And with that, I'd like to thank everyone, particularly Lorem, FRA, and Amtrak. And I put this picture up here so you can see the Commonwealth of Massachusetts with Martha's Vineyard down at the bottom, and Nantucket kind of off of the picture, but is represented by our undergraduate students. And with that, thank you very much. I really appreciate being able to give this presentation.
Carl, thanks so much. I'll go to maybe grab a couple of questions online, and then we'll get some from the room. How about that? And I don't think we have to use the mic. Is that correct?
Yes, please, so we can move.
read a couple of them. All right, the first question relates to the use of the FRA's track quality index and whether you use that as a comparison of any of your results to the TQI.
Not as of yet. I mean, we didn't use that.
Okay. Another question relates to the use that you're familiar with the MRAL technology that measures track reflection.
Yes.
Have you considered using that?
We would love to. I mean, we want to use as many different measurement techniques and indices. So both of those things are something that we would like to incorporate in future models. So the more information you have, the better off you are. And I just want to also point out, I've been also working with the University of Edinburgh on similar project using HS1 data and network rail data. And their data are different, but we are able to try to do similar things using a slightly different approach as to our decision process, but trying to go about it in the same way. So the idea is that if we can use as much input data as possible, we can get a much more robust solution and probably get a better prediction.
A lot of questions in the room.
This is primarily based on different passenger systems. Do you know what type of trains they're running over these? Are these like longer Amtrak lines or shorter tram lines?
I'm not allowed to say right now at this time, so I apologize for that. You know, the railroads are tight to the chest with their information.
All right, I have a question about the space curve. Which one do you use? Use the vertical space curve?
Yes.
And you got two space curves, one for each rail or one for the center line?
Center line.
Center line. And how do you generate this data? Is a high rail vehicle, is a autonomous system?
Probably, I think most were autonomous. Slide 12. This one.
Yeah, that's exactly it. I find it really interesting data, and you discussed that you were taking averages of the entire 200-foot section, and yet you were considering looking at it more discretely.
Yes. I mean,
and that makes sense given that mud spots and kind of pockets develop over shorter sections.
Absolutely, that was the main reason for it.
And so I was curious if you could just kind of talk about what that might look like and how it might impact the other slides that you were able to show.
Well, one of the things that we think it might do is if you use more of a peak value, like if you take a peak value for, and also relate it to where in the ballast it is. Is it underneath the tracks, center track? Is it off to the shoulder? You know, where is that fouling located? And if we take a peak value and identify where it's located, it could give you more information as to what's going on. Now, I mean, that in itself can be a real nightmare, right? I see you smiling back there going, yeah, try to do it. But I think that the peak value could be more important as far as identifying what the real level of localized problems would be. And also maybe it's not necessarily peak value, but zone. It could be, do you find adjacent zones having high values? Like in here, you can see we've got a zone in here of these middle 5 blocks as having really high values. Could that be something that you could lump together or do some sort of analysis to say, okay, we have an average value of 20.5, but we have a zone that is it looks like it's about 60 feet of averaging what looks to be about 24, almost 24 there. Is that going to be much more of a problem than the 20.5 would tell us?
There's just a lot that I thought you could do with this because we have so much data and we're taking this one aggregate value and
Yeah, well, you gotta start somewhere.
Absolutely.
Yeah, I mean, it'd be nice to be able to go right in, but it already took us long enough to figure out just how to to take the data and get it into a usable form that we could do the analysis. But I agree with you. I think that's just something that's very important to look at what happens specifically within more isolated zones, because it will identify those problematic areas.
Very fascinating, thank you.
I think 200 feet relates to TPI
Yeah,
as well.
yeah, I think you're right.
Yes, very nice presentation, Carl. Just to follow up on that question, what about the depth of fouling? I mean,
Yeah, I mean, that's something we would like to look at. I mean, I agree with you. That's something that actually we are looking at now. We're looking at.
so that can come into this picture of.
Right. It's just more parameters, right? The good thing with GPR is that that's the one thing that it can usually identify as the depth of fouling. It's really good at that. And so that could be another parameter to take a look at.
Great presentation. And in addition to that, do you think that you also combine geometry data? Because I mean, having a higher value in a curve, for example, should be more problematic than a tangent track.
Yes, I mean, the geometry data is a measure of what the shape of the track is, right? And obviously, if you have indicators within the geometry data that tells you that the track is in a problem situation, I mean, essentially that's what we're comparing. We're using those values to make the predictions as to what the rate of change would be, and if we're going to have the next inspection be a problematic one. And so, in a sense, if you're using the actual geometry data, the geometry data is also a measure of, a so closely associated measure of it not being fit, right? So I think that you have to be careful as to what you are using as an input variable. Is it truly a real input or is it used within calculating out our output value? I think we might have it as what's going in to calculate the output value.
What do you say about the standard deviation? Do you use a 200 feet moving window?
62?
62 feet?
Yeah.
Oh, is the moving window or is the NCO? When you get the standard deviation, do you use a 200 feet moving window?
Moving window.
200 feet?
Yeah.
Thanks so much for your time. If we find other questions, we may have to direct them to you to get further.
Sure, that would be great.
But thank you so much. Tremendous seminar. It's been a great day to spend with you, and now we have the social hour to spend with you, so we don't want to be late for that.
Yeah, absolutely not.
Thanks again.
I just want to say last thank you very much to all the people here at the University of Illinois. It's been an honor to be part of the William Hay seminar series. It's an outstanding series that's been, in the great legacy of the rail engineering program here, and I'm sure that you have a long history of many more seminars to come. Thank you very much.
Thanks.